At gases, we introduce a new observation or a new measurement, and that is your gas pressure. The pressure is the gas particles, because they have tons of kinetic energy, are now moving around and they impact different things. If they impact the sides of our container, they're exerting a force on the container. We can then measure that force and report it as a pressure. The more impacts we get, the higher the pressure. Right? So how do we then report the pressure? Right? There are a variety of different devices. The oldest version of it is manometer. Everyone can chat me? I think it's a manometer. I think it is. I don't know what it's called. But it's called something that measures pressure. Okay? And where this is ultimately coming from is atmospheric pressure. That was our initial discovery. Is that once we decided that we had gas particles and that we could feel things, we wanted to measure those. Okay? That measurement device first came in this kind of little format. So we've got a large beaker with a pool of mercury in the bottom of it. And then we have this tall cylinder. And we fill that tall cylinder with mercury and then put it inside the pool of mercury. What is going to happen to the liquid inside the tube? It should go down, right? We got gravity. Gravity pulls on things, and it should fall down. Interestingly enough, it didn't fall all the way down. In the case of mercury, it actually floated fairly high up. Why would it do that? Why would it stay elevated? Because of what? Temperature does have an effect on it. Okay, gravity says it falls down. If it doesn't fall down, what must be happening? Another force must be pushing the liquid up. Okay? But that tube is inside a big pool. The pool is pushing upwards on it? So like when we put just the container down on the ground, we just see the mercury come flying up out of the container? No, so the mercury is not exerting the force on it. What is exerting the force on that central stock? There's an invisible thing somehow coming through and pushing on the pool. It pushes on the pool to keep the pool in the container. But now since the pool is forced into the container, it can then force the mercury in the tube to stay upwards. Okay. So what we're reporting now is the pressure of this invisible thing that we can't see pushing on stuff that we can see. Right? That in and of itself isn't a big deal until somebody took this device and went somewhere else in the globe, right? Or noticed weather patterns and noticed that the level of mercury inside the tube changed. Okay? And where it was probably originally used for was predicting weather patterns. Okay? So if you've ever watched the Weather Channel, well, you don't have to watch the Weather Channel, watched any kind of weather station thing, they talk about high and low pressure fronts. What they're referencing is the pressure causing that tube level to change. Okay? That level or that pressure has massive effects on our weather patterns. Okay? What else could we do? Well, if we took this tube and went to a higher elevation, what happens? It drops. Why would the mercury in that tube drop if we move to a higher elevation? What's the stuff? There's less atmospheric air. So smaller arrows are pushing down, which means there's a smaller arrow pushing the mercury up, which then means it falls. Okay? And what we're doing is now just monitoring the effects of that pressure. We could say, well, it's really high pressure because the mercury's filled the whole tube. Or it's really low pressure because the mercury has fallen a whole bunch. Okay? So when you step on the balance in the morning, or whenever you step on a balance, And you look down and you go, oh, it's really high weight today. Okay. Or, oh, it's a really low weight today. Do we quantify a little bit more than that? Yeah. Guess what we have to do with pressure? Same deal. We'll have to quantify it. How did they quantify it? Well, it was based off of the height of the mercury. So they went and put a ruler next to it and said, well, today the mercury is at 10. Okay. Oh, tomorrow, we measure it, because we'll always measure tomorrow. It's at 12. What are the units on that? We said we put what up next to it? A ruler. So what would our units be? Whatever our distance measurement would be. What is our distant measurement? We could do inches. We could do centimeters. We could do meters. We could do millimeters. Right, which one do we choose? Depends which system we're working in, unfortunately. If we're in an English system, we could use inches. Right? Inches of mercury. That's what they're referencing. Okay? If we're in the metric system, we usually end up using centimeters or millimeters. It's typically millimeters. Why do we not use meters? Okay? That unit is now really, really large. The changes in pressure that we get, the mercury does change levels, but it changes levels by like that. For those of you who didn't watch, you can watch again, like that. Okay? So we're looking at very small distances. So I could say, well, that is a change in the meter unit. That was a change of 0.001 meters. Okay? That includes too many zeros, so we scale it out to a smaller metric unit system that we can get a little bit more precision and less zeros in our value. Okay? So that is then our unit system for pressure, which is awesome, because then what are you responsible for as students? Converting from one unit system to another for your pressure units. Sweet. Okay? But before we get into our unit system, we have an extra feature here. Notice that we used mercury. Could we do this with water? No one's taken like water, pinched the end of a straw, filled it up, put it inside a liquid? What happens to the water? It stays inside. Could we have used water? Yeah. It does something very, very similar. Water doesn't work, though, for this. The whole point of this is that it is exposed to atmospheric conditions. So this bottom dish has to be exposed to the outside. Right? So if we filled that with water, water must be exposed to the outside. Well, that's not a big deal, right? Because when we leave a container of water out on the counter, it stays there the entire time. It evaporates. What happens if the liquid in our pool disappears? Everything's going to drop because there's now less force pushing up because there's nothing there to push for the air to push against. Right? So when we're talking about the substance used in our manometer, it is a manometer, right? At least it bothered some, because I keep thinking like, manometer. I think it's a manometer. In our pressure measuring device thingy, okay, we need a liquid that does not evaporate. Okay, well, what's happening when we evaporate? What are we transitioning to? A gas. So we're looking at an inherent property of a material to stay a liquid and not go to a gas. Okay? That value or that thing, since it's a physical property for our material, gets a name. Okay? Anybody know what the name is for that? Look at the next slide. It's the vapor pressure. Did you find it yet? It is a manometer. See? I'm not as dumb as you all think. Okay? What is happening with our vapor pressure? Vapor pressure is the pressure of a gas. We'll go figure, it's got to be. Okay? But where did the gas come from? The gas came from the liquid. So if we look at, say, any liquid, come on, pencil. Here's my container. Here's my liquid. Actually, I'm going to go ahead and seal this in. Okay. And I've got my liquid down here. Okay. Closed system. Okay. And I remove all of the air, so it's just liquid inside this. What is that liquid going to do? What did water do? It evaporated. And by evaporating, what did it become? A gas. So it goes up to become a gas. Does it all become a gas? No, it's actually in what's known as equilibrium. Some of the liquid turns into a gas, and some of the gas turns to a liquid. That's known as the dew point. Okay, so, which we never see in Arizona. That's why we don't get fog, is because our dew point is so high, or so low, sorry. So what does that mean? Our liquid and gas oscillate back and forth between each other. When we're talking about the vapor pressure, it's how much of that gas is formed. Okay? So if I have a very high vapor pressure, what does that mean about the gas formed? Did I form a lot of it or a little of it? A lot, because I now have a lot of pressure. It is the pressure of that gas. So a high vapor pressure means lots and lots of gas. If we think back to our manometer, I should probably stop laughing at that, but it is kind of funny. Okay. Do we want a liquid that has a high vapor pressure or a low vapor pressure? It should be very low, because the whole point of it is that it does not turn into a gas. It needs to stay a liquid for this entire process, because it has to be exposed to the atmosphere the whole time. Okay? Mercury happens to have an insanely low vapor pressure, which is why mercury is used in a manometer. I don't know why I find that so cool, but I do. So if we're now looking at general substances, we can go through and monitor these. So if we go through, let's just switch up the diagrams at the bottom. If we take a look at the structure or the image on the left, what we're saying is we have one gas particle. Structure on the right, we have a ton of gas particles. Which one is mercury? Left or right? The left. Because the whole point of mercury is that it has a low vapor pressure. Nothing's in the gas phase. So there's our mercury. And water would be the one on the right. Okay. When they're talking about the vapor pressure, it's just how much gas particles are up there. And we could monitor that in a very similar system where we've got trapped atmospheric pressure over here. And what we're seeing is when we put in our liquid, how much does it change the elevation between those two? Is there an excessive force? Well, then it's a higher vapor pressure, because then what happens to this side? It goes up. And we can look at that difference to determine our vapor pressure. Okay? What happens to the vapor pressure as we increase the temperature? Well, what happens to the amount of liquid when you increase the temperature to the liquid? The liquid decreases because it's becoming a gas. The more gas we have, the more pressure we have, and the more vapor pressure we have. So vapor pressure and temperature are directly related to each other. Okay? What if we try and do the reverse? What if I want to dissolve a gas into a liquid? It's kind of a weird place to talk about it, but it works. Why would I lower the temperature?
Because you boiled water. You got a boiling point. So reverse.
What happened when I tried to dissolve a solid into a liquid? What did I need to do with the temperature? I needed to increase it. And yet you're telling me to dissolve a gas in a liquid, I have to decrease it. But it's all about solubility, the ability for one thing to dissolve in another. Why is it all of a sudden changing when we look at our temperatures? When we're trying to dissolve something in a liquid, we're trying to make that species look more like a liquid. To make a solid look like a liquid, what do I need to do? heat it up. To make a liquid, I don't know why I wrote T. Say heat. To make a liquid look like a gas, what do I need to do? Heat it up. So when I'm trying to dissolve a solid, that means take the solid and turn it into a liquid, sort of, really making it look like a liquid. Okay? I want to add heat because, well, solid needs to become a liquid. And the easiest way to do that is to add heat. What if I'm talking about a gas, though, and I'm trying to dissolve a gas? What am I trying to make the gas look like? A liquid. How do I make a gas look like a liquid? I'm now doing the reverse process. I have to cool it down. What if I added heat to my gas? Well, that's only going to take the stuff that's in the liquid and make it more gaseous. That's doing the opposite of what I want it to. So when we're looking at those trends, a lot of people say, well, they're opposites, they're exceptions of each other. They aren't exceptions. It's all about what you're trying to do. Okay? We're trying to make it look like a liquid. Well, where's a gas relative to a liquid? A gas is a higher energy state. If I want to make it look like a liquid, I need to remove that energy. I must cool it down. If I take a solid and I want it to look like a liquid, well, the liquid's at a higher energy state. What should I do? Add heat to get it to move across. Kind of makes sense? Okay. That's super relevant, just so you know, for like final exams or something. Units of pressure. So we talked about measuring our mercury, the height of our mercury. We can do inches of mercury. We can do millimeters of mercury. Okay? We can also do ATM, which is short for atmosphere. We could do torr. We could do inches of mercury. We could do kPa. We could do PA. Okay? There, etc. Because there's a lot of different pressure units depending on what system we're looking at. So you would be responsible for how you convert. So that's what they try to provide here. Inches of mercury equals how many ATMs? 1. Inches of mercury equals how many torr? 29.9 inches of mercury equals 760 torr. This chart allows you to do all of those conversions and set you up. Okay? For the sake of conversions, yes, you're responsible for that. For the sake of, do you need to memorize any of that? No. Okay? You're not responsible for dealing with any of those pressure things other than being told, this is what this equals, can you do a conversion? Okay? If you have to move into, say, 151, have fun doing all those conversions. Okay? Because they're also conversions, notice that we also have issues with sig figs. Some of them are exact, some of them are not exact. So we'd have to be careful with our sig figs when we go through and do those conversions. Okay? So let's get to the more interesting part. What are things that affect pressure? We've already talked about one. Temperature. Okay, what is the relationship between pressure and temperature? If I increase the temperature, what happens to the pressure of the gas? It increases. Because they have a one-for-one relationship, this is known as a direct relationship. Okay? I can also go through and add, because we saw this show up earlier, this goofy little, whoa, that was horribly drawn. That goofy little symbol, which means proportional. Okay? Directly proportional. I increase the temperature, the pressure goes up equivalently. If I want to make that an equal sign, what do I have to then add? That one's a little bit trickier. Not quite. I have to add in my equation some kind of constant. I don't know what the constant is yet, okay? But by including that constant, I can then see this relationship. Okay? And pressure will equal temperature multiplied by some constant. Okay? So pressure and temperature are directly related to each other. What else is pressure related to? The size of the container. We'll get to that one in just a second. Size of the container. okay, also known as the volume. So if I took a balloon and I tried to shrink the volume of the balloon by squeezing it in, what happens? It usually pops in your hands because what happened? The pressure built so much that it caused a structural failure within the balloon. Okay? What does that mean the relationship between our pressure and our volume are? As the volume decreases, the pressure increased. Can I write the same thing I did with the temperature? No, because that's saying they're directly related. They aren't directly related, they're indirectly related. Okay? As I increase one, the other decreases. How do I do that? Pressure is now proportional to 1 over the volume. If the volume value gets smaller, 1 divided by a small number becomes... Some people can see it, some people can't. This is why we have calculators. Let's test 2 values of volume. Volume equals 10, volume equals 1. What is the pressure when the volume equals 10? 1/10, 0.1. What is the pressure when the volume equals 1? 1. What happens to the pressure when the volume gets smaller? The pressure increases. Okay? It can be difficult to nail down those relationships because we're doing a division. That inverse thing tends to mess with people. So don't internalize it. Come up with examples to go through and do the comparison. Okay? So we now have 2 relationships. Pressure is directly proportional to temperature. Pressure is inversely related to volume. Okay? We had another comparison in the back. What was your comparison in the back? Elevation. What is happening when we change the elevation?
Pressure changes.
Pressure changes. What else is changing? Say that again? The amount of what? The amount of gas in the air. Okay? As I increase in elevation, the amount of gas in the air does what? Decreases. What happened to the pressure? Decreased also. So the amount and the pressure are directly related. Okay, so the pressure decreased and the amount. I could write out amount. That's an awful lot of letters. I wish I had an abbreviation for that. What are the units on that N for amount? We could arguably say whatever units we wanted, but let's not do that. ATM is a pressure. How do we determine the amount of a substance? What is the amount of people in this room? Our amount is typically units of moles. Okay? The number of particles is directly related to our pressure. We could have used grams. That does make things more challenging, and so let's avoid that. Okay? But we could use grams. So we know pressure is related to moles. We know pressure is related to volume. We know pressure is related to temperature. What is the relationship between temperature and the moles then? Okay. We could go through and start to now shuffle all of these relationships with each other. Okay. And eventually somebody went along and said, well, they're all related to some constant. How about I arrange them all and set them up so that I solve for whatever that constant is. Okay? In that system, if I solve for that constant, I'm going to define that constant to be R, and I notice that when I solve, I will get pressure times volume over the moles times temperature. When I arrange all of those terms, I get a value for R as my constant. What does that mean? What happens if I change the temperature? What's the value of R going to be? The same, because It's a constant. The whole point of a constant is that it doesn't change. If I change the temperature and R does not change, what does that mean has to happen? One of the other terms will have to change to counteract that. Okay? This is the power of this expression. Because it is a constant, under all conditions, I can now set up and solve for any one of these. Okay? What is that R value? It is 0.0821 atmospheres times liters divided by moles times Kelvin. What is the unit of pressure we're using? Atmospheres. Why would we pick atmospheres as our unit of pressure? Remember the unit table that we saw for pressure? What is our standard value for pressure in atmospheres? 1. That makes math really easy. That's why we picked it. Okay? If we look at all the other units, there are weird variations, different numbers of all sorts of different things. By defining our atmospheric pressure as 1, that can make our calculations a little bit easier to work with. Okay? What is our unit for volume? Liters. Because when we look at our ideal gas law, or sorry, our R value, the unit for volume is liters. Why would we pick liters for gases and not say milliliters? Not as small, kind of the right idea. When we're running reactions, right, we want a measurable amount. Okay? What is the mass of air? Not quite. The mass of air really large or really small? It is going to be dependent on the container because it's the density of air. And what is special about the density of air? It is insanely low. So to get a mass that's measurable, what do we need? A really large container. That's why we're using units of liters. It's to get the unit value up to something that we can measure reasonably. Okay? Moles is just our standard. How many particles are there? Okay? Which is relevant because when we think about pressure, pressure was the force exerted by our molecules. The more molecules, the more number of molecules, the more force because it's impacting. Is that a question? What happens if I take a small container and shove a whole bunch of air into it? What happens to the O2 in an O2 tank? The pressure goes up until eventually you can't stick any more gas into it because the gas particles want more space. Eventually they've gotten so close to each other that they're not a gas anymore.
Solid.
They're a liquid and then ultimately a solid. So as you shovel more gas particles into a container, if you don't change the volume of the container, those particles get closer and closer and closer to each other until eventually you're a liquid. Okay? The particles have gotten that close. What if you continue to shovel more particles in?
You just said it turns into a solid, but how does it turn into a solid?
Careful. We shovel more. I said it turns into a liquid. We shovel even more particles in. Now our particles can move less and less and less and less until eventually they can't move and now I'm a solid. So yes, I can take a liquid and convert it into, a gas and convert it into a liquid and convert it into a solid. It goes, oh, well you can't possibly do that. You mean I can't drop the temperature and the gas becomes a liquid? I can't drop the temperature some more and the liquid becomes a solid? What you're used to seeing is only changing the temperature. Does pressure also affect our phases? Yes. It has a massive effect on our phases. Okay? I can take a system, a container, and if I reduce the pressure low enough, okay, what happens to the particles inside it? Well, they find that there's more space, so they move out, and they start to become a liquid or a gas.
I know from experience that compressing air into a tank, you get heat. I guess it wasn't enough pressure to turn into a solid, obviously, but I'm just having a hard time.
So the idea is, how can you put so much in to get your phase changes? Okay, and yes, you have to increase the pressure depending on the substance a lot.
Are you talking about like super extreme?
It depends on the substance. Some substances are relatively straightforward and easy. Okay, if we think back to the physical and chemical changes video that you watched online, there was a GIF of a beaker, and in that beaker you saw this liquid that bubbled and then crystallized and then bubbled and then crystallized. Why was it bubbling? It was turning into a gas. Why was it a liquid? Well, it was a liquid. Then it crystallized. What is a crystal? A solid. Did you see any temperature associated with that? No. Why was it changing phases? If there's no temperature, what we changed was the pressure. Right? Pressure has a direct effect on our phases. Some phases have a larger effect than others. If I increase the pressure on a liquid, does it have much of an effect? No, because there isn't a lot of motion within a liquid. But if I increase the pressure on a gas, I can get a large effect when I increase the pressure enough, because I can force them into being a liquid. And yes, we get temperature changes due to this expression. Okay. What temperature do we use, or what unit do we use for temperature? Why Kelvin? It can't be a negative value. If I put in degrees Celsius, sometimes the temperature will be negative, which means R goes from being a positive value to a negative value. Okay, well, that's not possible, so one of the other terms would have to become negative. Can I have negative moles? No. Can I have negative pressure? No. Can I have negative volume? No. Okay? So when we're looking at our terms within gas laws, we have to make sure everything we're measuring is a positive value, because that makes our calculations significantly easier. That's why we run with kelvins, that's why we run with moles, liters, and atmospheres. Okay? The real power that comes out of this, and you may have heard someone say this, is they tried to go through and memorize it. Okay? And instead of looking at it as solving for R, they wrote it out as a nice, easy format, because the format shown is a fraction. They would go, oh, I don't like fractions, so what do we turn it into?
Multiplication.
PV equals nRT, often referred to as PIV-NERT. Yeah, exactly right. You'll hear people talk about PIV-NERT, particularly from general chemistry classes, because PV equals nRT. They're trying to come up with some way to memorize those relationships. If you have that, you have all gas laws. Okay? You have all of those laws that were defined up there in the beginning of your gas law textbook, your textbook on gas laws. You have Boyle's law, you have Gay-Lussac's law, you have Charles' law. All of those relationships get folded into R equals PV over NT. And even that, I'm going to say, well, why do I care about that? So now I can solve for any different condition. So if I'm given the moles, the temperature, and the volume, I can determine the pressure. So 4 things I can vary. As long as I'm given 3, I can solve for the last one. All right? The other big, powerful thing that we can do here is if I have a gas under conditions A, and I then change those conditions by, say, increasing the pressure, I can predict how it's going to affect the other things by moving to conditions B. How would I be able to predict that? Right? Well, what is R at conditions B? R would then equal what? Fair enough, but at conditions B. Give me conditions B. It would be the pressure at B conditions. It would be the volume at B conditions. The moles at B conditions. The temperature at B conditions. And because I know R is 0.0821, I can then simplify my expression to really say these two things are equal to each other. Right? Because I don't remember all those named laws. Anybody, what's Charles' law? Anybody have those memorized, the relationships?
Charles, the temperature of gas, or
What's that?
is it the temperature of gas that you
Charles says temperature and what?
of gas or
Okay, fine, I'll just cheat.
pressure is like directed?
Let's take a look at one of these laws. Charles, volume and temperature are directly related. So cool, Charles, thanks for making that observation for me. Okay. Since we now know our whole gas law system, and I know those are equal to each other. So Charles was saying volume, and temperature were related. Okay. Pressure A, volume A, moles A, temperature A. I'm concerned about volume and temperature. So I want to play with those. Because I'm only concerned about volume and temperature, what am I going to do to the pressure? I'll leave it the same. So when I change my reaction, the pressure stays the same. So what would my pressure B be? Pressure A. What would my volume be? B. What would my moles be? What would my temperature be? What happens to pressure A? Cancels out of the expression. What happens to moles? Cancels out. I can group like terms, and what do I end up with as a relationship? The volume of A over the volume of B is equal to temperature of A over, wow, soup, that's my fault. You were right. Temperature of B. What do you see on top there? Volume of A is proportional to the temperature of A. What do we see on the bottom?
Same, except for B.
What was Charles' law?
Volumes.
They're directly related to each other. The ideal gas law gives us all of those laws in one format. It's now just a question of saying, did that value change? No? Cancel it. Okay? The ideal gas law is awesome. This is why they reference Pivner. Okay? Really, what is the ideal gas law? It is a massive conversion factor. Okay? Once you have R is now your conversion factor that establishes all the units that you would need, and it's just a question of how you organize those units around that conversion factor. Most people find it easier just to write out PV equals nRT and use it as a formula as opposed to dealing with it as converting units. Okay? But all it is a conversion factor. Okay? So the volume of a container is doubled. Assume temperature and the moles are not changed. What happens to the pressure? So this is your turn. I want to know what happens to the pressure. So see what you can come up with. If you want, you can come up with the kind of quick thought process answer. Share that with the people around you. But you need to provide a numerical value-ish.
Yes.
So what's the answer? What happens to the pressure? It halves. So that's as far as we can get numerically. Am I recording? Yes. Okay. How do we figure that out? Okay. No, you can't assume they're all ones. I don't accept that.
Well, if they're the same, if you put in a value for the temperature and the mole and it was like a 1 and then you double, so
Never mind. I think I do accept that. Okay. So you're saying NA equals 1.
yeah.
What is NB? 1. Which then means the NA will cancel the NB. So said better, because the issue here is you're now arbitrarily picking 1. NA equals, whoops, that says NB. Now it says NB. Which then means when I go back and look at my equation up here, it's not NB, it's NA. 1 over NA equals 1 over NA. What happens to the NAs? They cancel out. What happened to the temperature? Stayed the same. So what is TB? Same as TA. What happens to the temperature? Cancels out. Did the volume change? Yes. So I can't cancel that. Did the pressure change? Yes. So I can't cancel that. So I end up with the expression PA VA equals PB VB. Where do I get the half from? The volume of the container is doubled. So VB equals 2 times VA. What is volume B? 2 times VA. Group our terms. Pressure B equals whatever the pressure of A is times the volume A over 2 times volume A. What happens to units of volume A? They cancel. What would I end up with? Pressure A over 2. Pressure goes down by a half. I don't need to know numerical values for all those things to actually bring in some quantitative information. That's the power of this system. Okay. Could we add quantitative system or information into this? Yes. Okay. And so one of the things that I find useful with these types of problems is to go through and specify them. Pressure A equals, I don't know. Volume A equals, I don't know. Moles A equals moles B. Right? They're the same thing. That's what the question tells me. Temperature A equals temperature B. By specifying that information, I can then start to decide how to plug and chug into PV equals nRT. Kind of make sense? Okay. How many moles of neon gas occupy 2.34 liters at STP? There are 2 ways to solve this. Hopefully you guys solve this the quick, fast way, but I'm then going to show you the slow, painful way. And with that, we'll come back. So, remember, you were told that you needed to memorize the conversion factor, that 22.4 liters is equal to 1 mole. When is that valid? When it's a gas. Is it a gas? Yes. When else does it need to be valid? At standard temperature and pressure. Standard begins with S. Temperature begins with and pressure begins with P. Are we at standard temperature and pressure and a gas? Yes. That conversion factor is valid. You can use that to solve this in one step. Okay? That's kind of what I'd expect you to do. Okay? The other option is going, okay, well, I know PV equals nRT. I'm being asked to solve for the moles, which is N. So N equals PV over RT. The last time I did this, I kept screwing it up. That's right, isn't it?
Yep.
Okay. The pressure was 1.00 ATMs. The volume, 2.34 liters, divided by R, which was 0.0821 ATM, liters, moles, Kelvin, times our temperature, which is 273 Kelvin. We punch this all into the calculator, and the calculator spits out the answer 104 moles. Okay. Our ATMs cancel, our liters cancel. Kelvins cancel. We'd end up with units of 1 over moles, which is moles. Okay, which is exactly what we're looking for. So that works. But here's the part that I actually want you to do. Okay? When you set it up, you probably took 2.34 and then divided by 22.4. Okay? So I want you to do a couple things for me. I want you to take 1 over 22.4, enter that into the calculator. What do you get?
How far are you up to?
Now just give me another one.
4. Yeah.
Now what I want you to do is take 1 divided by 0.0821 times 273. I don't trust your calculation. What's that? Wait, it's the same thing? Why does 22.4 liters equal 1 mole work? Because we're at standard temperature and pressure. What happens when you take standard pressure, 1 atmosphere, divided by 0.0821 times 273? You get the conversion factor of 1 mole equals 22.4 liters. Okay? They are identical to each other. The reason why most people don't want to go through and do PV equals nRT is you had to do more numbers. Okay? But you have to do more numbers that are always correct, as opposed to using 22.4 liters equal to 1 mole, which is only correct when standard temperature and pressure. The instant we're out of standard temperature and pressure, that 22.4 liters equals 1 mole is invalid, and yet students will still use it because we said, oh, it works. It doesn't work. It is awful. PV equals nRT, amazingly, sort of, always works when it is an ideal gas, okay, which is a pretty big caveat. When do you not work with an ideal gas? When you're in chemistry grad school. How many of you are planning to go there? PV equals nRT is lovely. Okay? The other things that come out of the gas chapter is kind of a random thing. Dalton's law of partial pressures. Remember, one of the assumptions was that our gas particles don't interact with each other. Okay? Which means Dalton's law becomes valid. I can take the pressure of each of those individual gases and add them up. That will then equal the total pressure, because each of those molecules exert some force. If I sum all of the forces, oh wow, I get the total force. Yes, that's what it means. Again, it only works for an ideal gas. That's all we're really saying, though, is you add this up, you get this. Okay? So we could take a sample of noble gas, helium, neon, blah, 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 yada, yada, yada. Helium, 125, neon, 45, argon, 158, krypton, 17. What is our total pressure? Add all the numbers. Do we need to solve that? No. Cool. Absolute zero. Okay. Out of the gas laws and kind of the physics associated with gases is where we came up with the Kelvin scale. We needed a way to measure the temperature that didn't all of a sudden make numerical values that are negative when they shouldn't be negative. That's why we have Kelvin. Okay? Kelvin tracks back to a theoretical absolute zero. Okay? At that point, we lose all motion. Okay? That's kind of the point of Kelvin. Simplify our calculations, make life nice and easy. Okay? As an interesting feature then, what is the lowest degrees Celsius? There is. What is the conversion between degrees Celsius and Kelvin? degrees Celsius plus 273 equals Kelvin. If I said 0 is as low as I can get in Kelvin, what does degrees Celsius have to be? Negative 273 is as low as we can get in degrees Celsius, and that's what they're showing in this chart. Okay, you can't get colder than that. You could do the same mental game with Fahrenheit as well. There is a minimal value. Okay? If we're looking at the Celsius and Fahrenheit scale, that minimal value isn't obvious because we're looking at a complete number line. Kelvin works out nicely because we don't have a complete number line. We're only positive values. That said, anybody want to be a physicist?
Not anymore.
Physicists are really, really awesome because what the physicists went through and did is some group of physicists and probably some chemists said, nah, I think I can get colder. And they have experimentally shown that they have achieved less than 0 Kelvin.
Wow.
Yeah, that one's kind of fun. It's an experimental kind of mathematical, like nuanced thing, because they started to get matter to do things that it shouldn't physically be able to do if we had positive values of Kelvin. Okay. The interesting feature beyond that too is in the process of getting to negative Kelvin, they did not pass through absolute 0. Yeah, that's another just brain fudge. Okay. But yeah, kind of neat. Just thought I'd throw that out there because it's funny.
Like they use the word fudge.
Yeah. Well, I don't know what else I could say. I'm being recorded. Okay. Limiting reactant. Okay. Bless you. So now what we're doing is skipping back and forth. Okay, so we went through chapter 8, then we jumped into 9, then we jumped into, I think, 13 for molarity, then we jumped into 10 for gases, and now we're back to 9. Okay, so we're taking all of those concepts and smashing them all together into one glorious, awesome test. Yay. What is going on with our limiting reactant concept? We've also already addressed this kind of aspect. Okay, grilled cheese sandwiches. Okay, we're going to make a simple sandwich. 1 slice of cheese, 2 slices of bread. Clearly this has problems because there is no mustard. You gotta have mustard. So, slice of cheese plus 2 slices of bread equals 1 sandwich. You have 5 slices of cheese, 8 slices of bread. How many sandwiches can you make? 4. Okay. And remember all this? How do we go through and do this? We have 5 cheese. I want sandwiches. How do I convert? 1 cheese, 1 sandwich. Do the calculation, I get 5 sandwiches. What's the case for the other one? Was it 8 bread? And to get rid of bread, 2 bread equals 1 sandwich, which gets me 4 sandwiches. So you all said I could make 4 sandwiches, but 5 is bigger than 4, so I think I can make 5 sandwiches.
That'll be an incomplete sandwich.
We could just cheese.
Which I've also done that too. That's actually a really good sandwich. You just use cheese. A little bit of cheese, a little bit of mustard. Perfect.
Gross.
Why can I not make 5 sandwiches?
Because
I'm out of bread. Bread is a limiting reactant. It limits how much I can make. So I go through and I run the calculation and I'll look at the numbers that come out and I will pick the smaller of those 2 numbers as my maximal value, which is really weird because I'm taking a small number to be the biggest amount. Okay? But that's how the limiting reactant concept works. Okay? I can then say that bread was a limiting reactant. I could also say that cheese is in excess. I have too much of it. Okay? So if we scale this back, cheese plus bread equals sandwich is roughly equivalent to what? A chemical equation. Okay? And when we looked at chemical equations, we looked at conversions and making products and all that other fun stuff, which means we can then go through and apply this same concept of limiting reactant concept back to chemical equations. Okay? And we can vary the amounts of 2 reagents, and we'd have to decide how much product could I maximally get out of an experiment? And I would do that by calculating these things out. In that question, I could say, I only produce 4 sandwiches. I could also say, what's the limiting reactant? Bread. I still have to do all the calculations. I'd go back, see the one that generates the smaller number. The one I started with on that is my limiting reactant. I could also ask, what is the reagent in excess? Cheese. And the last fun one, which typically doesn't get asked unless you're in 151, how much reagent in excess do I have? Okay. I'd have to go back through and ultimately convert the 8 bread into cheese, which would be 4 cheeses. I started with 5. 5 minus 4 is 1 cheeses. Okay? That typically sucks. Okay? But it is a common question in 151. Not such a common question in Gen Chem. So let's scale this out. Yeah, we get the sandwiches. How do we do this with a chemical reaction? 2 moles of sodium hydrogen carbonate are mixed with 2 moles of water and 1 mole of carbon dioxide. How many moles of sodium hydrogen carbonate are produced? Why is this question already more difficult? There's 3 things instead of 2 things. Okay? And when I had 2 things, how many equations did I have to solve? 2. Now that I have 3 things, how many equations do I have to solve? 3. Okay? So I will start with, did you say what's wrong with you? Oh, man. This semester, people are just like sniping at me. Did I already make the comment that I had a student call me a dick in my organic class? That was awesome.
Like out loud?
He was hoping to say it a little bit quieter under his breath. I have somewhat decent hearing. It's kind of hilarious. Oh yeah, I said something. Yeah, it was kind of awesome.
What did you say?
Just asked, did you call me a dick? Just asked, clarification. You got to know. Moles of sodium carbonate, are those equal to moles of sodium hydrogen carbonate? No, so what do you have to do? Unit conversion, moles, sodium, carbonate on the bottom, moles. Sodium hydrogen carbonate. And yes, I did just accept the name call. That's understandable. Where do we get our conversion factor from? Coefficients from the balanced equation. What's the coefficient in front of sodium hydrogen carbonate? Sodium hydrogen carbonate. 2. Coefficient in front of sodium carbonate? 1. Brooke asked a very good question. Is the equation balanced? Was I that much of a dick again? No, I balanced it. Okay. So we solve and I get 4. I can make 4 moles of sodium hydrogen carbonate. Someone said no. Why'd you say no? There were 3 equations we had to solve for all 3 equations. I will give you a minute. Okay, so we've got our basic setup. What coefficients go up in our red equation?
2 over 1.
2 over 1. How many moles of sodium hydrogen carbonate could I make? 4. See, I told you it was 4. How about the last one?
2 over 1.
2 over 1.
That makes 2.
So you get, oh crap, I guess I was wrong. 2 moles of sodium hydrogen carbonate. The most we could make?
Is 2.
2 moles of sodium hydrogen carbonate. What's our limiting reactant? Carbon dioxide. Our reagents in excess? Water and sodium hydrogen carbonate. Okay? We have to solve all of these to go through and determine this. This is why we have to have a solid method as we crank through them. This was a relatively straightforward one because it required how many conversions? 1. What if I'd given you grams? You wouldn't like me. That's fine. You have to add in more conversions. Okay? So, sorry for taking a picture. Dang it, did you get it?
Barely the bottom.
Okay, that's good, because I just got rid of it. Okay. We bring in the idea of a percent yield. The whole point of a percent yield is to normalize your results. Have you guys done the copper lab yet? I don't think so. You go digging some dirt and you find 5 grams of dirt. I go and dig in some dirt somewhere else and I get 500 grams of dirt. Who found the better dirt? Depends on what? How much did I have to dig versus how much you had to dig? Right? We can't look at an absolute value. We have to have a standard to compare against. If my 500 grams of dirt was found by digging through everywhere except your location, and your location was 5 grams of dirt, I think you won. Right? So we have to have a comparison. That's our percent yield. The actual, what did we actually get? What could we theoretically have gotten? Right? The actual will always be experimentally given because that's what you did. The theoretical is something that you have to calculate. Right? How do we calculate it? Same way we did the limiting reactant. Right? For a chemical equation, we go through and predict how much could I possibly have gotten. And I know you're excited to get out of here, but I'm going to leave you with one awesome question. Percent yield, not that one. That one. There it is. A 50.6 gram sample of magnesium hydroxide. Already you should be saying, shut up, Mike. But number 2, starts with grams. Is reacted with, no, it's a chemical equation. 45 grams of hydrochloric acid. At the end of the reaction, a chemist was able to record a dry mass of 60.0 grams of magnesium chloride. What was the percent yield? Right. This is a big, long problem. I would like you to attempt this over the weekend. We'll talk about it on Tuesday.